Hello guys, good day and welcome to today's lecture. I am Udom Philemon of Genius Creed, and in today's lecture we'll be solving a simulation that involves recycle. Okay, so let's get into it. So our simulation problem, our problem statement involves the production of ethyl chloride using ethylene and HCl with copper chloride as the catalyst, right? So we'll be getting into our simulation environment immediately, right? So first off, we'll be adding our components to the component list, right? So we have ethene. I'll use the formula. Okay, let me use. Then we have HCl. Then we have ethyl chloride. Then we have nitrogen. Okay, so we've added our components. For fluid package, we'll be making use of Robinson. Okay. Okay, so the question says the feed stream is composed of 50 mole percent HCl, 48 mole percent ethylene, and 2 mole percent nitrogen at 100 kilomole per hour, 25 degrees Celsius, and 1 atm. So the first thing we'll do in our simulation environment is to specify the feed stream. So for the feed stream, we have temperature of 25 degrees Celsius. Then we have 1 atm pressure, 1 atm, then molar flow of 100 kilogram mole per hour. Then we go to composition. We have ethylene of 48 mole percent, which is 0.48. Then we have 0.5 for HCl. Then nitrogen is 0.02. Now, we won't have any value for ethyl chloride because it can't be in the feed stream. It's actually the product, so it won't be part of the feed. Okay, so we've specified our composition. Okay, so moving on, then it says since the reaction achieves only 90% mole conversion, the ethyl chloride product is separated from the unreacted reagents and the latter is recycled. Also, it says the separation is achieved using a distillation column where it is assumed that a perfect separation is achievable. Okay, so before we proceed to specify the reactor, we'll first add a mixer. Now the work of this mixer will be to mix both the feed stream and the recycle stream that will later be coming into the process. So let's change this to feed. So this mixer will actually be mixing both the feed stream and a recycle stream that we'll be adding later. So just specify this for now. Our outlet is mix out. Now then we have feed. So for now this is fully specified, but we'll be making adjustments to it later. So now that we have specified the mixer, the next thing will be to specify the reactor. From the problem we said, it says the reaction achieves only 90 mole percent conversion. So we'll be creating a reactor that produces the ethyl chloride. We'll be using the conversion reactor, right? But before we specify it, let's go back to the simulation basis manager to create a reaction. So we'll go to reactions, then we'll add reaction. We are choosing conversion because conversion was given in the problem. So you specify the reaction. So we have ethylene and HCl to give us ethyl chloride. Nitrogen is inert. Sorry. So the equation is balanced. Then we specify our conversion of 90%, right? Yes, 90% conversion. So we have 90. We have 90. The conversion has been specified. Okay. So we add our set to fluid package and it's fully specified. The heat of reaction has been specified as well. So we can go back to the simulation environment. Okay, so we'll now be specifying our reactor. So our feed is mixed out. Then we could use vape as the top and leak as the bottom. Then we need an energy stream. So we'll be creating an energy stream as well. Then we'll add our reaction set. So we have set 1. So now we need to specify the outlet temperature. so that Hysys can calculate duty, right? So go to worksheet, and for vapor we'll be specifying 25 degrees Celsius. Yeah, so our reactor is fully specified. So we have specified the reactor. Okay, so we reduce this a little. That's okay. So let's go back to the problem statement. So it says the ethyl chloride product is separated from the unreacted reagents and the latter is recycled. The separation is achieved using a distillation column where it is assumed that a perfect separation is achievable. Now, to actually simulate a distillation process where perfect separation is achievable, we will need to use the component splitter of the model palette, right? So go back to the palette. We'll be making use of the component splitter. Okay, yes, so this is what we'll be making use of. So we'll be specifying the component splitter, right? So the component splitter would actually separate the mixture entirely. That is, it would separate a particular substance from the others in the mixture, right? So that's why we are making use of it. So we have our we'll specify our energy stream as Q2. Then our feed is VAP. Okay, so our top would be OVHD. Then the bottom can be BTTM. Now it says unknown splits. Okay, so now let's go back to the problem statement. Now it says the ethyl chloride product is separated from the unreacted reagents. Now let's go back to our simulation. Now from the worksheet, the composition. Now we want to separate ethyl chloride from ethylene, HCl and nitrogen, which are the unreacted components. Now nitrogen is unreacted because it is not part of the reaction, it's an inert. Then the ethylene and the HCl are actually the ethylene and the HCl that are left after the process had taken place. So technically we are separating ethyl chloride from these three others, and that's why we are making use of the component splitter, so that it can separate it entirely without leaving any part of the ethyl chloride with the rest of the substances. So we'll go back and specify the split. So for the splits now, let's see. Okay, so for the splits, we want ethylene, we want ethylene, HCl and nitrogen to come out from the top of the column, while ethyl chloride will come out from the bottom. So for the overhead, we'll be specifying we'll specify 1. We'll specify 1 for ethylene, HCl, and nitrogen, while for ethyl chloride we'll specify 0, because we want ethyl chloride to come out from the bottom of the column. So it will be 1 at the bottom and 0 at the top, while the rest are 1 at the top and 0 at the bottom. Now we go back to worksheet to specify pressure. So for pressure, we are using atmospheric conditions. So we'll specify 1 atm, 1 atm, Then we'll also specify temperature as 25 degrees Celsius. 25 degrees Celsius. Okay, so our component splitter is fully specified. So now let's go back to worksheet. So you see, for our bottom product, we have just ethyl chloride at the bottom, just ethyl chloride. So we have fully specified our component splitter. So we move on to the next thing. So it says to prevent the accumulation of inerts in the system, 10 kilomole per hour is withdrawn in a purge stream W. So to simulate this portion of the problem, we'll be making use of a T. Now, the work or the job of a T is to separate a mixture depending on the specifications. So it does the opposite of a mixer, right? So we'll be specifying the T now. Okay. So we'll be specifying the T. The T will separate or release some part of the mixture out and then give us the other part, which will now form our recycle. So our inlet will be overhead. Then let's see. Okay, it says the process to prevent the accumulation of inerts in the system, 10 kilomole per hour is withdrawn in a purge stream W. Now it still says show the effect of the flow rate of the purge stream W on the recycle R. So for the T, we'll be creating two outlet streams. So we would have R as our first stream, and then we'll have W also, right? So the problem said 10 kilomole per hour is withdrawn in a purge stream W. So we'll be specifying 10 kilomole per hour as the flow rate of W, right? So we'll have 10 here. So we have 10 kilomole per hour here, right? Then we will now create a recycle block for R that will now feed us back to the mixer, right? So now we'll go to the manipulator section to get the recycle unit. So we'll be using the recycle unit. So our inlet to the recycle will be R. Inlet will be R. Then outlet will be recycle. Okay, so outlet will be recycle. Now, this recycle stream now is what is fed back to the beginning of the process. So the mixer here actually mixes both this recycle and the feed, right, for the process to continue. So that was why we had to make use of a mixer in the first place. So we'll come back here and we add the recycle stream to the process. Okay, so our process is complete. Okay, so at this point we are done with simulating the process. So now we are about to solve the problem that was stated in the problem statement. So I think okay, so we are done simulating the process at this point. So now it's time to solve the problem. So let's go back to the problem statement. So it says show the effect of the flow rate of the purge stream W on the recycle R and on the composition of the reactor feed. Now, to actually solve this problem, we would need to use the Aspen Hysys case study tool to actually understand this particular relationship that is being asked about. So we'll be creating two case studies actually to solve it. So you just go to home, then you click on case study. So we have it on our screen. So first we are going to do W against R. That's the first. So you click on add, then you click on find variables. Now this is the independent variable. Now the independent variable is the variable the user specified. That's the independent variable. Now W was specified by me, so it is an independent variable, right? So that's what you are going to specify first, the independent variable, the one specified by the user. So you have W, now W, and we are going for molar flow, right? Molar flow. So we add molar flow and we are okay. Then for the dependent variable, that's the one Hysys calculated. So in this case, it will be R. We are doing W against R. And still on its molar flow. Molar flow, yes. Molar flow. Done. So we have specified both variables. Let me just confirm. Show the effect of flow rate on recycle R. Okay, that's okay. So it's correct. So we are specifying W against R at molar flows. So the next thing is to specify the setup. So I'll be making use of 0 kilogram mole per hour for start, then end will be 13, then step size of 1. So I'm making use of 0 to 13 kilogram mole per hour as my range and a step size of 1. So after specifying all this, you click on run. Okay, so once it's done running, you now click on results, right? So in the results, you can actually view the table of values that was generated by Aspen Hysys. Then you can also check the plots. Now this is the plot of that's R against W. Yes, R against W. So to show the line, you have to click on this and maybe click on case 1. So this is actually the relationship of the molar flow of the recycle against the waste, which is W. So as you can see, at the beginning there is an initial increase up to maybe around 1 kilogram mole per hour. Then from 1 to 6 is slightly unchanging. The R values is slightly unchanging, is quite constant, but then from 6 to 10 it begins to drop until it gets to 10, then it starts dropping quite steadily until it now gets to, I think, 13. So at the 13 point, it's now at 0, right? So this is the relationship between the recycle stream and the waste stream. So this is the first solution to the problem. So the second one says show the effect of the purge stream W on the composition of the reactor feed. So again, we'll be using the case study tool. So we'll be creating another one. Let's see. Yeah, case study. Yes. So we'll be creating another case study. So to create another case study, you click on add. And yes, you can create more than one case study in a particular simulation case. You can actually create more than one. So again, our independent variable is W. So we'll be finding W. And it's still molar flow. Then the dependent variable is let me check, the reactor feed, right? Reactor feed. Okay, the reactor feed is feed. That's this one. Oh no, it's mix out. Yes, let me check. The reactor feed is mix out. Okay, so it's mix out, and this is mix out here, and it says the composition of the reactor feed. So we are going to make use of mole fraction, and we are making use of master component mole fraction. So we'll be adding each of them individually, right? We'll add each of them individually. Done. Okay, so I think we are good to go now. Let me see. Nitrogen, HCl, ethene, and ethyl chloride. Okay, we are good. Then we'll specify the setup. We'll still be making use of 0 to 13. Then step size of 1. Yes. So we'll run again. We'll run the procedure. Okay, so Once you are done running, you go and check your results. You check your results. Then you check your plots. Okay, so you have them like this. Okay, so you could from here you could actually get different the different plots for each of those components in that reactor feed, right? Because they are actually, it's actually individual, so you have to actually specify which of them you want to view, right? So you have the composition of those components against the molar flow of W, and this is how it goes. So at this point we have come to the end of today's lecture. I hope you enjoyed it. Do well to comment, drop your comments, like and subscribe to the channel so that you can get future notifications of when new videos come up. Thank you and have a nice day.